Welcome back to the Computer Architecture Lab, the show where we break down the latest research in computer architecture and systems. Today, we're diving into a paper that was just presented at ISCA 2025, one of the top venues in computer architecture. The paper is titled, Lightweight Cache Replacement for Instruction-Heavy Workloads, and it introduces a technique called PACIPV. It comes from a team at Texas A&M University, Texas A&M International University, and the Barcelona Supercomputing Center. There's a lot to unpack here, so let's get right into it. First, the problem. Every modern processor has a memory hierarchy. You've got your fast, small caches close to the CPU, and then the big, slow main memory far away. The last level cache, or LLC, is your final line of defense before the processor has to go all the way out to main memory, which is extremely slow by comparison. The job of the cache replacement policy is to decide which data to keep in that LLC and which to throw out when it gets full. Get that decision right and your program runs fast. Get it wrong and you're constantly waiting on memory. The traditional approach is something called LRU, least recently used. It's the textbook answer. Evict whatever you haven't touched in the longest time. It works reasonably well in some cases, but it has real problems with thrashing and scanning patterns, situations where a flood of data blows through the cache and pushes out blocks you actually needed. Researchers have known about LRU's limitations for a long time and have proposed more sophisticated replacements. The issue is that the really good ones, like a policy called Mockingjay, come with enormous hardware costs. Mockingjay needs around 127 kilobytes of extra hardware budget for a 4-core system with an 8 megabyte LLC. It uses sampled caches, reused distance predictors, estimated time of arrival counters, multiple complex logic components. That's a serious barrier to getting adopted in real commercial chips. So we have this tension. Simple policies don't perform well enough, and complex policies are too expensive to build. And there's a second dimension that makes this even more pressing. The workloads running on modern data center and commercial processors are becoming much more instruction-heavy. Traditional cache research has focused a lot on data-heavy workloads, but today, instruction cache misses are a significant source of performance loss. Server workloads, cloud applications, large software stacks, they all have massive instruction footprints. The existing complex replacement policies were mostly designed with data-heavy workloads in mind, and they don't always translate well to instruction-heavy scenarios. That's the gap this paper steps into. So what's the key idea behind PACIPV? The paper builds on a concept called Insertion and Promotion Vectors, or IPVs. An IPV is basically a small lookup table that tells the cache how to update the priority of a block when something happens to it, when it's inserted, when it gets a hit, things like that. The clever part of PACIPV is twofold. First, they build their IPVs on top of RRIP, which stands for Re-Reference Interval Prediction, rather than on top of LRU. RRP uses a coarser notion of recency. It groups blocks into just a few categories, like near immediate, long, and distant reuse, rather than trying to track the exact order of every access, the way LRU does. This coarser classification turns out to be more accurate at the LLC level, because intermediate caches have already filtered and disrupted the fine-grained access ordering. Second, and arguably more important, PACIPV uses two separate IPVs, one for demand accesses and one for prefetch accesses. This is huge. Modern processors use aggressive prefetchers that speculatively pull data into the cache before the program actually asks for it. Those prefetched blocks behave very differently from blocks that arrive because the program directly requested them. Prior work like SRIP treats both kinds of accesses the same way. PACIPV says, no, we should handle them differently. And the paper uses an instruction prefetcher called EIP, the Entangling Instruction Prefetcher, to show that when you co-design the replacement policy to be aware of prefetching, you get much better results. Let's walk through how PACIPV actually works. Each block in the cache has a 2-bit re-reference prediction value, or RRPV, the same as in standard RRIP. There are 4 possible values: 0, 1, 2, and 3. A value of 0 means the block is predicted to be reused very soon. A value of 3 means it's likely dead, it'll be evicted first. When the cache needs to evict a block, it looks for one with RRPV equal to 3. If none exists, it increments all the RRPVs in the set until something hits 3. Now, PACIPV defines 2 IPVs, each of length 5. The first 4 elements define the promotion policy. When a block with a given RRPV gets accessed, its new RRPV is given by the IPV. The 5th element defines the initial RRPV for a newly inserted block. When a demand access hits in the cache, PACIPV uses the demand IPV to look up the new RRPV. When a prefetch access hits, it uses the prefetch IPV instead. Now, how do they figure out which IPVs to use? Each element of an IPV is a 2-bit number, so each IPV has 5 elements, giving you 1024 possible IPVs per vector. With 2 IPVs, you'd naively have over 1 million combinations. But the authors apply smart heuristics to prune the space. They require that every RRPV value be reachable, and they require that a cache hit can never demote a block. After pruning, they're left with about 4,032 reasonable pairs, small enough to search exhaustively on a compute cluster. They simulate every pair on a training set of workloads, rank them by instructions per cycle, and pick the best. The winning pair in their experiments was a demand IPV of 01103 and a prefetch IPV of 01003. And importantly, this search is done once at design time, not at runtime. This is a static policy. You do the search offline, burn the 2 vectors into the hardware, and you're done. No online learning, no sampled caches, no complex predictor tables. That's a major practical advantage. All right, let's talk results. On instruction, heavy workloads from the Championship Value Prediction Suite, evaluated in the ChampSim simulator configured to mimic Intel Alder Lake, PACIPV achieves a 3.3% geometric mean speedup over LRU when paired with the EIP instruction prefetcher. That outperforms RRIP, which gets 2.2%, and it matches or slightly beats Mockingjay at 3.2%. Without EIP, PACIPV actually leads the pack at 3.0%, ahead of Mockingjay's 2.8%. Now, those numbers might sound small, but in the cache replacement world, that's significant. We're talking about the last level cache, just one component in a massive pipeline. Squeezing even a few % out of LLC replacement translates to real performance gains at scale. And here's what makes it even more compelling: the hardware overhead. PACIPV requires only about 12 kilobytes per core, the same baseline as RRIP. Mockingjay, by contrast, needs 24 kilobytes per core, plus 32 kilobytes of extra metadata. SHIP needs an additional 6 kilobyte predictor table on top of its baseline. So PACIPV is delivering top-tier performance at a fraction of the hardware cost. The authors also tested PACIPV on data-heavy graph analytics workloads from the GAPS benchmark suite. Even using IPVs trained on instruction-heavy workloads, PACIPV still outperforms RRIP and SHIP, and comes within about 1.2% of Mockingjay. They tested sensitivity to LLC size as well, halving it and doubling it, and PACIPV remained robust across all configurations. There was also a counterintuitive finding worth highlighting. PACIPV actually has more LLC misses than some other policies, but it still achieves higher IPC instructions per cycle. The authors hypothesized that PACIPV is keeping the right blocks in cache, the ones that matter most for performance, while allowing less critical blocks to be evicted. They validated this by showing that PACIPV achieves the lowest L1 instruction cache demand, mislatency among all policies tested. So it's not about minimizing total misses. It's about minimizing the misses that actually hurt. So what does this mean for the broader field? First, this paper is a strong argument for simplicity in cache management. There's been a trend in recent years toward increasingly complex, ML-driven, predictor-heavy replacement policies. This paper shows that with the right framework, IPVS plus RRIP plus prefetch awareness, you can get comparable or better performance with dramatically less hardware. That's a message that resonates strongly with industry, where verification cost, area budget, and power consumption are real constraints. Second, the idea of treating demand and prefetch accesses differently is really powerful. Prefetchers are becoming more aggressive and more accurate, especially for instructions. The interaction between the prefetcher and the replacement policy is an underexplored design space, and this paper shows there's a lot of performance left on the table. Third, the methodology itself is a contribution. The exhaustive search over a pruned, manageable space of IPVS is much more principled than using genetic algorithms on an enormous space. You know you've found the global optimum within your search space, and the space is small enough that a human can look at the resulting vectors and actually reason about why they work. As for open questions, the authors point out that using more than 4 recency positions could unlock better performance. There's the idea of dynamically selecting IPVS per workload using set dueling, which could let PACIPV adapt on the fly. And there's the question of co-designing IPVS across the entire cache hierarchy, not just the LLC, but L1 and L2 as well. All exciting directions for future research. So to wrap up, this paper presents PACIPV, a lightweight cache replacement policy for instruction-heavy workloads. It uses 2 small vectors, one for demand accesses and one for prefetches, to guide how the last-level cache manages block priority. It matches or beats far more complex policies like Mockingjay, while requiring a fraction of the hardware. It was presented at ISCA 2025, and it comes from Texas A&M University with collaborators at the Barcelona Supercomputing Center. If you're building a real chip and need a replacement policy, you can actually verify and implement without blowing your area budget. This paper should be at the top of your reading list. Thanks for watching. We'll link the paper in the description below. If you found this breakdown helpful, hit subscribe, and we'll see you in the next one.